All right, in this video, we are simplifying equations to determine if they are linear or nonlinear. So what I have up here, and what you'll want to do is go ahead and write down the information that I have. So it might be a good idea to be listening and then pausing and writing it down as you're making sense of it. If you have any questions, it'd be a good idea to write some notes along the side so that you can do those, you can ask me those questions when you come back into class. All right, so a linear equation has a constant rate of change, and so we're going to simplify the equations that I have below to determine if they have a constant rate of change. The formula used is y equals mx plus b, and the m here is the rate of change. That's the number that's being multiplied to the x, and the b is the beginning value or the y-intercept. Okay? An example of nonlinear equations would be something like y equals x squared. It's nonlinear because the x is being squared or it has any power. If it was x cubed, it would be nonlinear because that power or that exponent is going to manipulate the rate of change, and it's not going to have a constant rate of change. Y equals 3 to the power of x. Well, the x is an exponent here, so therefore it is nonlinear. Y equals 4 over x. Well, anytime x is in the denominator position, it is nonlinear. Because think about if you substituted in 0 for x, you can't do that operation, right? You can't divide anything by 0, and you'd end up with an error on your calculator. And therefore, it would not have a constant rate of change. Okay, so knowing that if we simplify things down and they look like one of these, they're going to be nonlinear. And if they look like this form, they're going to be linear. Right, so let's look at this first one. You're going to want to copy that down, and again, pausing this as you work through it. Simplifying it so that we can find the rate of change and the y-intercept. First, I'm going to distribute this 3 here, and so what this is saying is 3 times x plus 2. So I'm going to draw that by just drawing out arrows, and I'm just going to simplify what I have so far. I've got y equals 3 times x is 3x. 3 times 2 is 6, so that's plus 6. Okay, so I just did that operation. And I'm going to bring down these other parts. Plus 4 minus x. Okay. Highlighters here if I need them. So the only thing that I did from step 1 to step 2 was distributing that 3. Now I'm going to combine like terms. I'm going to square things that include x. And I'm going to square in that subtraction sign because that's really a negative 1x. And then I'm going to circle my non-x's. And we're going to combine the like terms. So if I had colors here, I would be combining this and this because those are like terms, and then I'm combining this and this. Okay? Bringing this down, I've got y equals 3x minus x is 2x. 6 plus 4 is 10. Y equals 2x plus 10. And so if it's linear, let's go ahead and write the rate of change and the y-intercept. So the rate of change we show is change of y over change of x, and that is 2 over 1, because it's just 2, and divided by 1 is the same thing, so 2 over 1. And then the y-intercept equals coordinate pair 0, 10. Okay. So I simplified that down, and I was able to see that this equation, even though it didn't look linear up here, it looked very complicated. When I simplified it, I got to here, and I was able to see that it has a rate of change of 2 to 1, and it has a y-intercept of 0, 10. All right, using that information to go to the next one, y equals x, parentheses x plus 2. So same thing as I did here, I'm going to distribute that x. It becomes x times x, and x times x is x squared because exponents are repeated multiplication, so that's x times x, and that equals x squared. Okay, and then x times 2 is plus 2x, and that equals y. It's in simplest terms. Just like I couldn't combine non-x's with x's, I cannot combine x squareds, x's with an exponent with x's that don't have exponents. So therefore this is nonlinear, and I'm going to draw an arrow to y. It is nonlinear because the x is squared. So just like we saw up here, x is squared. So that piece right there makes it nonlinear. Okay? And I'm going to write here nonlinear. All right. Next one, things getting a little complicated here in this one. This is yx. That's the same thing as saying y times x equals 10. Y times x. And so we want to rearrange it so it becomes y equals. So in order to do that, we have to undo the operation of multiplication here. We want to get that x, we want to divide out that x because right now it's being multiplied to y. So I do that by the opposite of multiplication is division. And when I do that, it cancels out my x's. And I end up with y equals 10 over x. And I would see in this one that this is nonlinear. And it's nonlinear because the x is in the denominator. Okay. Now, if the x is in the numerator, that's okay. That still has a constant rate of change. You would see that if you were to do some inputs and outputs with tables, that it would still be okay. But when the x is in the denominator, it's nonlinear. And the last one, simplifying this out. So I've got a 4x minus 3 plus I've got a 2x plus a 6. Now I cannot combine those because one has an x and one doesn't. And I cannot combine these because one has an x and one does not. So what I'm going to do is I have a total of 6 x's. I've got a 4x. And because this is all addition, it doesn't really matter that there's parentheses. I could take the parentheses away and it would mean the same thing. So 4x plus 2x is 6x. And then I've got a minus 3, and I've got a plus 6. And so that becomes 6 minus 3 is plus 3. And I would see that as I simplified that out, I now have a y-intercept, and I have a rate of change. And if I were to write this out, I'm going to write change of y over change of x, and that change of y is 6 over 1. And the y-intercept is 0, 3. There's that y-intercept, and here's that rate of change. Okay, so go ahead and as you're working through these, you are stopping, you are writing your notes. This is going to go into your toolkit, and we're going to use it to work on our work when we come back into class tomorrow.